Hi everyone, welcome back to Chem Story. Today we're going to dive into how alkynes react with HX, in other words, hydrohalogenation. It's a really useful reaction because it lets us add both hydrogen and halogen across a triple bond. We'll look at how the mechanism works, what kind of products are formed, and how factors like regioselectivity and the amount of HX affect the outcome. Alright, let's jump in and take a closer look. Alright, so how does this reaction actually work? When HX adds to an alkyne, it goes through an electrophilic addition, just like we see with alkenes. And it follows Markovnikov's rule. The hydrogen adds to the carbon that already has more hydrogens on it. But here's the interesting part. We're not just adding HX once. If there's excess HX in the reaction, it adds twice to the triple bond. The first addition gives you a vinyl halide. Then the second one, it gives you a germinal dihalide, with both halogen atoms landing on the same carbon. And along the way, we form a vinyl carbocation intermediate, which is super important for controlling where each atom ends up. That's what drives the regioselectivity of the whole reaction. Now let's take a closer look at how the mechanism works. First, the alkyne grabs a proton from HX, and that forms a vinyl carbocation. Then, the halide ion X- comes in and attacks that positively charged carbon. That gives us a vinyl halide as the initial product. But the reaction doesn't stop there, not if there's more HX around. The alkene that just formed reacts again. Another proton adds in, creating a new carbocation, and then another halide jumps in to finish the job. And that's how we end up with a germinal dihalide, with both halogen atoms attached to the same carbon. Let's briefly summarize it step by step. Step 1. The pi electrons in the triple bond go after the hydrogen in HX. That forms a new CH bond, and we get a vinyl carbocation. Step 2. The halide ion X- comes in and attacks that carbocation, forming a CX bond. Now, if there's excess HX in the reaction, the whole thing happens again. Another proton adds, then another halide, all on the same carbon. And that gives us a germinal dihalide, which is actually a pretty stable product. Now let's talk about regioselectivity. Just like with alkenes, hydrohalogenation of alkynes follows Markovnikov's rule. That means the hydrogen adds to the carbon that already has more hydrogens, and the halogen goes to the more substituted carbon. When we're dealing with terminal alkynes, this pattern becomes even more obvious. Both hydrogens from the two HX additions end up attaching to the terminal carbon. So the halogen atoms both go to the internal carbon. Here's something interesting to think about. Let's compare how HX adds to alkynes versus alkenes. In alkenes, the carbocation that forms is fairly stable. It's sp2 hybridized, so the positive charge can spread out more easily. But in alkynes, the carbocation, we call it a vinyl carbocation, is way less stable. It's sp hybridized, so the positive charge is held much tighter, and that cranks up the energy level. So even though the final products might look kind of similar, the intermediates are very different in terms of stability. And that difference affects how easily or how quickly the reaction actually happens. Speaking of reactivity, let's talk about how fast this reaction actually happens. Since vinyl carbocations are pretty unstable, you might expect this reaction to be a lot slower than hydrohalogenation of alkenes. And yeah, in theory, that's true. But in real lab conditions, the difference in speed really isn't as big as you might expect. Even though the vinyl carbocation isn't very stable, the reaction still moves along at a reasonable pace. So yeah, it's slower than with alkenes, but still totally practical for most situations. Now let's talk about the kinetics of this reaction. Based on experimental data, the rate law comes out to rate equals K times alkyne times HX squared. That means the reaction rate depends not just on the alkyne, but also on two molecules of HX at the same time. And that points to a termolecular mechanism with 3 different species involved in the rate-determining step. That kind of setup usually points to a concerted mechanism, or at the very least, a really well-organized transition state. So this reaction might not be a simple step-by-step process after all, and that's exactly why scientists are still looking into the details today. So based on everything we've seen, the regioselectivity, the rate law, and the fact that vinyl carbocations are so unstable, a lot of chemists think the classic two-step mechanism might not tell the whole story. Instead, There's growing support for a revised pathway called AE3, which stands for termolecular electrophilic addition. In this model, the protonation and halide attack happen at the same time in one concerted step. And by doing that, we skip the vinyl carbocation ion altogether, which makes the whole reaction a lot more reasonable. This idea is backed up by theoretical studies, and it helps explain how the reaction works so smoothly, even though the intermediate seems way too unstable to form. Before we wrap up, let's go over a few extra points about this reaction. First, the rate trend follows the strength of the acid. HF less than HCl, less than HBr, less than HI, so HI reacts the fastest. Second, this reaction doesn't involve any rearrangements. That means the product structure is nice and predictable, which really helps when you're designing a synthesis. And finally, the reaction is exothermic. It gives off energy, which helps push the addition forward. All right, that brings us to the end of our deep dive into hydrohalogenation of alkynes. We looked at the mechanism, the regioselectivity, and why vinyl carbocation ions are such tricky intermediates. We also explored how the reaction might happen through a concerted pathway, and how kinetic data gives us clues about what's really going on. It's a great example of how a reaction that looks simple on the surface can have a lot more going on underneath. Thanks so much for watching, and as always, I'll see you in the next Chem Story video.